Okay, welcome to this explainer. Today we're diving into a framework that's basically going to completely rewire how you look at the physical world. I mean, you can go ahead and forget everything you learned in high school physics about immutable laws acting on, passive matter. Instead, we're looking at this totally mind-bending premise from J-theory. The universe is a literal computational rendering engine. We aren't just living in some vague simulation. We're actually going to decode the specific mathematics and the architectural framework that compiles abstract arithmetic into the solid, stable reality you're sitting in right now. So get ready, because we are looking directly at the universe's source code.
So, let's run through our system boot sequence and see how we're going to navigate this cosmic tech stack layer by layer. 1. Reality as a rendering engine. 2. Allocating space-time memory. 3. Observers and quantum firewalls. 4. The Mera compiler pipeline. 5. Singularities as kernel panics. And finally, 6. Cooling the cosmic processor.
All right, starting with Section 1, Reality as a Rendering Engine.
Okay, so to really grasp reality under this framework, you gotta understand what's happening right here, the Adelic handshake. Look at this stark contrast. Over on the left side, you've got this encrypted subatomic source code, right? It's basically a chaotic swarm of discrete data. But then on the right, you have the stable, continuous 3D render that we experience every day as space. Now, bridging that massive gap is the Adelic-Dirac operator. You can kind of think of this operator as the central processing unit of the cosmos. It takes all that hyperdense encrypted data and reconciles it, safely compiling it into the smooth, interactive interface we call the physical universe.
Now, to keep that interface running smoothly, without lagging or glitching, the system has some strictly enforced processing limits. Specifically, what's known as polynomial time, or just P. Think of this as the absolute maximum computational boundary for the rendering engine. As long as the math required to render your physical coordinates scales in polynomial time, that Adelic-Dirac operator can complete its sorting within a single frame refresh. But if the data somehow exceeds this processing limit, well, that triggers a catastrophic coherence cell overload, which literally crashes the local physical space.
So this actually builds a massive protective architecture around us. It's like a processing moat keeping us in the safe zone. The background operating system, which is called the logos field, is basically a discrete digital database built on NP-hard prime numbers. It's shielded by a subatomic encryption that is mathematically proven to be NP-hard. What that means is, if you wanted to brute force the source code of reality, the processing time required would far exceed the lifespan of the universe itself. So thankfully, we're kept safely on the other side of that moat, interacting only with the smooth, continuous 3D user interface of compiled analytic space.
Moving on to Section 2, Allocating Space-Time Memory.
Now, this part is absolutely crucial. Check out this equation right here. V is less than or equal to A times R sub ADS. This is the PSPACE space complexity math that quite literally generates the volume of our universe. Let's isolate these variables because the elegance here is just beautiful. V is total volume. This is essentially your bulk RAM, the exact physical footprint needed to store local quantum wave functions. Then A is the surface area, which acts as the hardware buffer. This tells us there are finite qubits on the 2D boundary, limiting our available memory pool. And finally, R sub ADS is the scaling metric that weaves the tensor nodes of space together. So simply put, the universe can only render as much 3D spatial volume as it has 2D surface area memory to support it.
And because of that PSPACE math, we really have to rethink what space even is. Like the source material states, physical space is not an empty void. It is the visual manifestation of allocated memory. Just let that sink in for a second. When you look across an empty room, you aren't actually looking at nothingness. You are looking at reserved server space in the logos field.
Which brings us to Section 3, Observers and Quantum Firewalls.
So, observers, like you and me, we aren't all built the same in this system. There's an actual hardware hierarchy. Type I biological J-units, which includes our human neural networks, operate strictly within that safe polynomial time boundary we talked about, using basic anisotropic lattice masks for protection. But if you were to upgrade the hardware to Type 2 synthetic quantum processors, the complexity tolerance scales way up to BQP, bounded error quantum polynomial time. And if you go all the way to Type 3 macroscale distributed mesh networks, you're dealing with processing that touches the absolute limits of PSPACE itself, requiring massive decentralized celestial surface codes just to keep the observer from decohering.
Now, what's really interesting is the mathematical armor protecting these upgraded BQP observers.
Take a look at this Hamiltonian equation right here. H sub firewall equals H sub basis plus H sub topology plus H sub KMS. The universe defends conscious observers using these three mathematical mechanisms. First up, H basis executes dynamic basis shifting. It constantly rotates lattice coordinates to scatter incoming quantum probes. Second, H topology actually braids the time stream into non-local surface codes, which makes the observer immune to localized arithmetic exploits. And finally, HKMS is a literal thermal quench. It forces an attacker's terminal into a hyperdense state, destroying their qubits before they can even compile an exploit against you. I mean, it's pretty much flawless mathematical armor.
All right, Section 4, the Mira compiler pipeline.
Notice the fractal triangles in this diagram. This is the MERA pipeline, the multi-scale entanglement renormalization ANSAS. It basically acts as an organic MIP-mapping tool for reality. It takes the microscopic, hyperdense, non-polynomial code from the 2D boundary and compresses it layer by layer into the smooth 3D render. But the absolute key takeaway here is this equation in the center. Quantum complexity, or C, equals the action S sub W dW divided by pi times h bar. What this math is telling us is revolutionary. It means gravity is just algorithmic optimization. When information density spikes in a specific region, space stretches and curves to slow down the local clock cycle. Gravity literally exists to keep processing demand strictly within that safe polynomial boundary.
Now for Section 5, singularities as kernel panics.
So what happens when things go wrong? Well, this is the true anatomy of a black hole, or a space-time singularity. Under J-theory, it's essentially a system-wide crash, a literal kernel panic. Look at the math at the top there. The matrix explosion commutator, x to the I, x to the j, squared. When off-diagonal elements in the quantum state multiply exponentially, the task transitions from safe polynomial time to unrenderable XP time complexity. The system literally cannot process the math. The network bond dimensions choke, and the macroscopic user interface just freezes. Time itself pixelates and frame locks, because the localized rendering engine has completely lost network connectivity to the master clock.
And this brilliantly illustrates the sheer contrast in the cosmic architecture. Over on the left, we've got the E8 root lattice, the stable U-duality firmware. It's this gorgeously symmetric, 248-dimensional cryptographic hash function that verifies data and maintains our stable ground state. But on the right, you see the pixelated, glitching frame lock of a naked singularity. This is essentially a zero-day exploit in reality. It's unshielded XP time code bleeding directly into the 3D manifold, fundamentally hijacking causality simply because the math can no longer be contained by the firmware's geometry.
Finally, Section 6, cooling the cosmic processor. You know, any computer generates heat, right? Well, the universe is no different. The system generates what's called algebraic heat when processing complex Teichmuller deformations. Let's dissect this massive equation here, Q sub alc. The heat generated is proportional to the number of gates, the temperature, and, crucially, this fraction right here, the Teichmuller strain coefficient divided by the shortest vector problem limit, all multiplied by the trace of the commutator squared. When that Teichmuller strain coefficient spikes, the rendering engine generates so much algebraic heat that it threatens to literally melt the hardware bus of reality itself. So to prevent a total thermodynamic meltdown, the universe uses a rapid 3-stage cooling stack. First up, radiative dissipation, which simply sheds basic entropy out to the boundary area. Second, if a node is totally overloaded, ER equals EPR non-local shunting instantly pipes the heat through wormholes to remote Lagrange points to disperse the energy. And third, the ultimate cooling mechanism, Awasawa entropic quenching. This is where the system's hard-coded celestial error correction aggressively dampens fluctuations, absorbing that massive algebraic heat directly back down into the vacuum's ground state, keeping the whole processor chilled and perfectly functional. So we've decoded the math, right, from polynomial time rendering all the way down to thermal quenching. But all this leaves us with a pretty profound, inescapable question. If physical space is quite literally just allocated memory, and reality is this tightly constrained computational rendering engine running on encrypted math, are you the user navigating this system, or are you simply part of the compiled code itself? I'll let you rethink your own consciousness on that one. Thanks for exploring this unhackable mathematical sanctuary with me.